Good morning everyone, how is it going today? My name is Alejandro and welcome to my channel. Here we talk a little bit about programming and coding in general. Today we're going to be going through a data science project, one in which we will see linear regression and how to apply it in R. Okay. In order to follow this tutorial, it's recommended that you already know a little bit what linear regression is and how it works. Although I will explain it a little bit pretty quick at the beginning. If you want to deepen your knowledge in linear regression or just get a quick introduction before actually watching this video, I recommend that you check out my article that I published on Medium. It's titled A Simple Explanation of Linear Regression, and then at the end of the article there will be this video explaining pretty much how these concepts are applied in R. Okay, so without further ado, let's get right into the project and let's create our linear regression model. Okay, so let's go. So let's get started, okay? We're going to be doing this in RStudio to manage our project, and we're going to be using this dataset right here, okay? I will paste the link in the description so that you can download it and follow along. The idea is that you have an e-commerce customer dataset, okay? You just have to click on download it. And once you download it, you're going to have to unzip it. And once it's unzipped, you're going to have to add it to your project. And how do you do that? Okay, 1 second. There you go. So here I have my folder of my project. I created the data folder, and inside the data folder, I'm just going to add the unzipped file here, right here. I'm just going to rename it. I'm going to rename it e-commerce users. There you go. So now, as you can see, we have here our files, and here we have e-commerce users inside our data directory. Okay, and this is the one that we're going to be using. So first of all, we're going to have to create a new R script. I'm just going to call it main.r inside our regression tutorial. It's right here, and now we can start analyzing our data. Okay, sorry about that. Just gonna set this in silence mode. There you go. So first of all, what we're gonna have to do first is import our data. Okay, import data and setup. There you go. Just gonna add some divisions right here. There you go, like that and like that. There you go. And first of all, we're going to import our data. To do that, we just use the read.csv command, and then we just tell it where our data is located. Since we're working inside a project, it's important that we use a relative path. So this means that it's relative to the current position of my file, so which is main R. And then I just write data, because the current position was in main, and then we enter data, and then inside data we just open e-commerce.users. I don't know what this file doesn't have a CSV extension, but it's a CSV file, so I mean it should be alright. I'm going to run that one, and let's view it. Okay, so let's view the data. There you go. So here, this is how the data looks like. We have an email column, we have an address column, we have an avatar apparently, which is probably the name of the user. Average session length. We have the time on the app, because I mean these are users that are spending time on an e-commerce application and website. Okay, and we have the time they spent on the website. We have the length of the membership that they've had in this e-commerce website, and they have the yearly amount spent in that e-commerce platform. Okay, and the idea right here in this project is that we're going to try to predict, based on this variables, like the time they spend on the website, the time they spend on the application, and the average session in these platforms, we're going to try to predict we're going to try to predict how much they are going to spend in the platform, okay? And to do that, of course, we're going to be using a linear regression. Not of course, but this is just what the video is about. We could use another model, but we're going to be using, I'm going to be showing you how to do this with linear regression. So let's continue analyzing, like just getting an idea of our data. To do that, we're going to check the structure of the data. And I'm just going to move myself over there so that you can see what's going on here. So here we have an email variable. We have 500 observations. That means that we have 500 rows. Each row is called an observation. We have one variable which is the email, and it's a character variable, which means that like just a string. Each value is a string. Then we have the address, which is also a string. The avatar, which is also a string. We have the average session length, which is a number, and that's in minutes. The time on app that they spend daily, I suppose. The time on website, and the length of the membership in months, if I'm not mistaken. Let's check that out. Do we have an explanation for that? All right, let's just suppose that it's in hours. E-commerce, linear regression. This is a very popular data set anyways, that you should be able to find it. Alright, so the data set is having data of customers who buys clothes online. The store offers an in-store styling clothing advice sessions. Customers come to the store, have sessions, meetings with personal stylists, and they go home and order either on the mobile app, the website, or on the clothes they spent. All right, so actually the session means the length of the meeting with a personal stylist. It's important that you understand what each variable actually means, that you can actually give a valuable insight with this data. Then they can go home and order either on mobile app or on the website the clothes they actually want, okay? And we're going to predict how much money they are going to spend in that order. And we're going to be trying to predict it with these variables. I don't have the actual measurement, but as you can see for the data, the time on app is probably in minutes. The average session length is also in minutes, because they went physically to this place and they spend some time in the place. Which is in minutes, 34, 31 minutes. Then we have the time they spend on the website, and the length of the membership in months that they have. All right, so yearly amount spent in dollars. There you go. So now we have seen the structure of the data. What we can check right now is the summary of the data. Let's see. So we have the email, all right, address, characters, avatar. We have the minimum session length to be 21, the maximum to be 36. So it's around 30-minute sessions for each client. We have time on the application. The shortest one was 8 minutes, and the longest one was 15 minutes. They do tend to spend a little bit more time on the website, apparently, with 33 minutes and 40 minutes. Length of the membership. We have some that have had the membership for 0.2 months, and others that have had the membership for nearly 7 months, and the yearly amount spent, okay? So there you go. Now that we have a little bit more of an idea of how our data looks like, now we can actually start plotting the data to try to see correlations on what is, just to try to get a feel of what the data, how it's correlated and represented, etc. Okay, so we're going to add a new section that's called Create Plots and search for insights. How about that? All right, so for the plots, we are going to be using the basic R plotting system, and we can also be using ggplot. So I'm just going to add here the library ggplot2. If you don't have ggplot, you're going to want to install it, and to install it you just run install packages and then you just run ggplot. Okay. Alright, so first of all, let's ask ourselves, is there a correlation between the time spent on a website and the yearly amount spent by each user? Okay, and we can do that with ggplot. Let's see. Let's find correlation between time on website and yearly amount spent. So let's see if there is. Now to plot to make a plot in ggplot, we do ggplot. We're gonna pass in the data as the first argument, and then we're gonna say that the x-axis is going to be the time on website. There you go, like that. And then the y-axis is going to be the yearly amount spent, which is what I have right here. There you go. Just gonna copy paste it so that I don't make mistakes. And let's add some, let's make it a point scatter plot. Okay, so we're going to add a geometric point fill, and let's just say add a little bit of color. We're just going to say that the color is going to be orange. Okay, just add a very quick title so that we know what this plot is going to represent. So this one's going to be time on website against yearly amount spent, like that. And then let's add some labels as well. To add labels, you just do xlab and then you run the function with the name of your label. So this is going to be, the x label is going to be time on website, and the y label is going to be the yearly amount spent. Okay, this is just a label. So let's run that one. We have an error apparently. Data correlation between error in ggplot. Could not find function ggplot. Yeah, because I did not run my library. Now if I run it, I still have an error because y label is not supposed to be with an uppercase. There you go. No, there you go. So here we have it. Here we have the scatter plot. Now, as you can see, there doesn't seem to be much of a correlation between the time they spent on the website and the yearly amount they spend. The client spends. This looks very, very scattered, and it doesn't look very relevant to our study. So, that's already an insight. Let's check for other correlations, all right? Let's see the correlation between the average session length for when the customer went to the store to actually try out the clothes and to take the measurements, etc., versus the yearly amount spent. So let's add again a ggplot. I'm just going to copy this one right here. I'm just going to paste it down here. So it's going to be the data, but instead of being X time on website, it's going to be session length. Where is the session length name? Here it is. Average session length. And Y is going to be the yearly amount spent. And here's going to be session length against yearly amount spent, time on website, session length. That's going to be my X label, and the Y label is still yearly amount spent. Okay, I'm going to run this, and as you can see, we have a little bit more of a correlation. It's very, very thin. It's very, very small. But you can see that the longer the session, they tend to spend a little bit more. Okay. It's definitely different to the one that we saw about the time they spent on the website. This one does look a little bit more correlated. So, all right, so that's already a pretty good insight. Let's see, what else can we do? How about we do a pair plot of all our variables, okay? Of all continuous variables. This is important. I mean, this is just a basics of data science and data visualization. If you're going to use a scatter plot, both variables have to be continuous. I mean, they have to be numeric. They don't have to be categorical. Okay. In that sense, since the session length is a number and the yearly amount spent, you can actually plot a number to it. But if it was just a categorical variable, you would just see a column of points, which is, I mean, it's useful sometimes, but like it's not a real scatter plot. So there you go. What we're going to do right now is we're going to pair plot all the continuous variables together to try to find more correlations to see how this looks like. Okay. The function to code this is pairs, and we're going to pass in the data, and instead of passing all of the data, we're just going to subset some columns of the data, and to do that we're going to say which columns we actually want. So we're going to just say the we're gonna say the average session length. Of course, this one is continuous. We're going to pass in as well time on app because it's continuous too. What else are we gonna pass? We're gonna pass in time on website because it's continuous. We're gonna pass in length of membership because it's continuous. And last but not least, we're gonna pass yearly amount spent because that's actually the response variable that we're looking at and that we're trying to predict. Okay. So now that we have passed in the data that we are going to be analyzing, let's just add some more, just a little bit more parameters. Let's say the color first, and I'm going to keep it to orange because I don't know, it looks alright. PCH, let's set that to 16, and the labels, yeah. Let's just add some labels. I'm just going to add, no, you know what, we can just do without the labels for now. But yeah, I mean, if you wanted to add some labels, you can just add a vector here and just add pretty much the same thing as you were adding up here and do, yeah, so this one is going to be average session length, but instead of like it having a like a variable name, you can actually name it with a more understandable name without having all the dots in there. I mean, just to show you how it works, but I'm not going to do it here. And I am actually going to add a title, and the main is going to be pair plot of all continuous variables. There you go. And now if we run this one, we see that we have a pair plot, and actually I'm going to zoom in a little bit on this one to actually show you what is going on. So here we have pretty much the same as we were doing before, but for all of the continuous variables. So you can see a little bit more clear how this data set behaves. So first of all, we have our response variable. We set it at the end, so that's pretty convenient because I mean we can see more clearly which variables have a correlation with it. Okay, so let's say we have that the length of membership is actually the most correlated one. As you can see, the way this pair plot works is that you have your yearly amount. I mean, the variable right here is the x-axis and the variable right here is the y-axis. Okay. Sorry, this one is the x-axis and this is the y-axis because this one's right here. So that means that this one's right here and this one right here is right here and this one's right here. Okay, so x is length of membership and y is yearly amount spent. So here you can see that as the length of membership increases, the yearly amount spent increases as well, which is kind of logical, I guess, because I mean the more time you have spent being a member of this store, of this community, the more time you have had to actually buy things. Then we have that the time spent on website doesn't really seem very correlated. So I mean it's here, but it doesn't look extremely good. I don't know. Here we have the time on the app. This one does look a little bit correlated to the yearly amount spent. And then last but not least, we have the average session length. And it does look a little bit correlated too. So there we have it. Now we have seen now we have more of an idea of what our data set actually looks like and the relationship between different variables. Okay, so that's pretty important. What we're going to do right now is we're going to wait a second. Just let me add a new section right here, and we're going to explore the selected variables. Okay, let's see to see what they actually look like themselves without actually looking at the correlations. So let's see, exploring the selected variables. There you go. I mean, this can be useful if you're going to be using different models. Some models do require normality, some models don't, but I mean, this is just to see. Okay, the condition for it being for fitting a linear regression is that the data has to have a linear relationship. I mean, that's an assumption. But right now, let's just explore the selected variables. Okay, so I mean, just as a matter of exercise, let's see if our variables are normally distributed. Okay, so is the variable normally distributed? There you go. Now to do this, we can actually use, I mean, what I would recommend that you do is just use the basic histogram from R. You can do it like this, data, and then you say length of membership like that. And this is going to show you a histogram of your length of membership data. Pretty important, you can use a histogram because your data is continuous. I mean, your variable is continuous. If it wasn't continuous, you would use a bar plot instead, right? So this is the histogram. It does look a little bit normally distributed, so that's looking pretty good. I'm just going to show you how to do that on ggplot pretty quick. So you would do ggplot as well, and same just as before. You would. I mean, I guess I could have just stored this in a variable, but I'm just going to copy it like that. So you can do ggplot data, and then we're not considering the time on the website, we're considering the length of membership. And we're not going to have a y variable because we're just measuring just the histogram of one single variable. And we're going to do geom histogram. There you go, like that. And I mean, the idea of using ggplot is that you can customize it a little bit more. So I'm just going to add a color. Let's say that it's going to be white. Let's say that the fill is going to be orange, because just to keep it consistent. And actually you can also, I mean, you can also do this in regular R function, but you can set a bin width. So here, as you can see, that our bin is 0.5. If we don't set it, I'm not sure to what it will default. So it wasn't to 0.5, it was to 0.25 apparently. No, I don't know what the bin size is right here, but I mean, you can actually customize it. Just set bin width, like not bit, bin width, and let's set it to 0.5. If we hit enter, then we have a similar histogram to what we had before in our R function, just that R is a little bit quicker. I mean, the base function is a little bit quicker, but it's less customizable. Okay, there you go. So it does seem to be normally distributed. So now, just pretty quick, what we're going to be doing is we're going to be plotting this same variable as well, because it's the one that we're going to be choosing for our linear regression model. And we're going to be plotting it with a box plot this time. All right. So instead of using the histogram function, we're going to use the box plot function like this one. It's the base function from R, and we're just going to pass in our variable, right? So let's say length of membership, like that. Let's run it, and we have our box plot over there. So we can see it actually does look normally distributed. And we do have some outliers, but they're not very, very far away. What else do we have? Let's do the same thing, but with ggplot, okay? We're going to be doing pretty much the same thing as we did up here, but instead of adding a histogram, we're going to be adding a geom box plot like that. There you go. And how about we add a fill color of orange, just to keep things consistent again. There you go. And I'm pretty sure that's all. There you go. As you can see, we have our box plot now. And I mean, it's horizontal, of course, because I passed in the variable in the x-axis, but if I pass it in the y-axis, we see that it actually takes the form of the previous plot that I showed you before. I'm just gonna leave it right here as an horizontal one. There you go. So now that we have chosen our variable that we're going to be using for our linear regression model, we're actually let's just actually fit our linear regression model to our variable and our response variable. Okay, so let me add just a new section right here, like this. There you go, like this. And here, this one's going to be called fitting a linear model. There you go. First of all, I'm just going to attach the data so that this means that whenever I run a function, I just have to type in the name of the variables, not actually mention that they come from this data. I mean, it just saves me time, I suppose. So I'm going to create this linear model fit. I'm going to store it in a variable called lmfit1. And the function to actually create a linear model is lm for linear model. And it takes as an argument, the first thing that you have to write in here is the response variable that you expect to get. So for example, we expect to get the yearly amount spent, like that. And after that, you write a tilde like that one. And here you write in the variables, or the variable that you expect that are the predictors, okay? So right here we have chosen length of membership as our predictor, so I'm going to pass it in like that. And there you go. So now let's run that one. I'm going to run attach data. I'm going to run lmfit like that. So now we have lmfit, and you can see that we have lmfit up here as a list of 12 elements. And actually we can start looking at lmfit and to see, to our linear model and try to get some insights from it. Okay, so let's just check the summary of it. The summary of our lmfit, we just wrap the variable that you were using to fit it. And let's just run that one. Just gonna move myself over here and let's see. So here we go. We can see the function that we called, and we actually did call. This one is the response that we expected, and this one is the predictor. We have the residuals as well. We're going to analyze the residuals in just a moment, but let's focus on something else, okay? Remember that right here, what we're doing is we're finding, not this one, here you go. We're trying to find this right here. Nope, sorry, not that one, this right here. So this is a linear regression with just one predictor. The one predictor we have is the x right here. And here we have the coefficient of x, which is the weight of our variable. And we also have the intersect with y. And of course the predictor. The intersect is just when y equals 0, okay? When x equals 0. So there you have it. Here we have our intercept, which is $272, because of course we're talking about the predictor, which is in dollars, the yearly amount spent. And we also have the length of membership. The coefficient of this one is 64. That means that wait 1 second. Yeah, it's 64. That just means that it's it's I mean it's positive, and it's a positive relationship with the length of membership. We also have some more variables right here. We have the standard error, which is a pretty important measurement. We have the t-value for the student t-test, and you also have the significance with the p-value. Okay, as you might remember from your statistic classes, if the p-value is lower than 0.05, that means that we reject the null hypothesis, and that also means that this variable right here is actually significant. Okay, which means that actually the length of membership is significant to our linear model. So this seems to be working correctly. Since we have 3 stars right here, that means that it's very significant. Here we have the significance codes. 3 stars means very significant, and it goes all the way to 0 stars, which is not significant. We also have the residual standard error and the multiple R squared, the F statistic. So I mean, this is how you measure how well fit your model is. So there you have it. That's how we have already fit our model. But how about we actually plot it? All right. So let me show you how it looks when plot. I'm just going to plot it pretty quick like this. I'm going to go yearly amount there, and just add length of membership right here. There you go. PLT, it's not PLT, it's plot, like that. So there you have it. I mean, this is pretty much just the same graph that we had just a moment ago. Okay, it's nothing new. But I'm just going to add the linear, the regression line that we have just created. And to do that, I just use this function ABLine, and I just pass in my linear model, which is lmfit1, the one I stored right here. I'm just going to color it red. How about that? There you go. So here you have, this is our regression line. As you can see, we have our intersection at, where was it? 272. So here is our intersection, and the coefficient of our length of membership is 64. And that basically describes this line. So that is how you do a linear regression for one single variable. Something that you're going to want to do right now is to analyze the residuals, because linear regression assumes that the residuals that you get are going to be normally distributed. If they're not normally distributed, that means that there's a problem with your model. So what does it mean that the residuals be normally distributed? The residuals are the distance, but I mean, you can just see it as the distance between the points and the distance between the points and the regression line. Okay, and there are many different ways to actually test if the residual, if the distribution of the residuals is normal. I'm just going to show you 2 ways of doing it. One of them is with QQ-plot, and the other one is the Shapiro test, Shapiro-Wilk test. So let's check that out. I'm going to add a new section right here. And this one's going to be residuals analysis. Remember, this is pretty important for your linear regression analysis. You're always going to want to check the residuals. So the first thing I'm going to do is I'm going to create a QQ-plot. If you're not familiar with what a QQ-plot is, I encourage you to check that out. But I mean, I'm just going to explain that pretty quick anyways. So you're going to want to pass in the residuals here. So residuals, and that's the function that you're going to want to use. Residuals is with an S, sorry about that, residuals. And you're going to want to pass in the model that you just trained, which is lmfit1. There you go. And that's basically just created a normal QQ-plot for us. And what does that mean? So basically QQ-plots just take the distribution of your data and they divide it into different quantiles. And then you also have a theoretical quantile, which is the normal distribution. And then you you also have a theoretical distribution, which is the normal distribution. And you divide this theoretical distribution into the same amount of quantiles. And then you just put all the quantiles for the normal distribution right here, and then all the quantiles for your sample distribution right here. And then if all of them are actually, like, if the normal quantile goes with the, I mean, you plot the normal quantile with your sample quantile, and if all of them are like 1-to-1, then that basically means that your distribution is completely normal. Okay, I guess another way of saying it is just by plotting a histogram of it. So we can just say hist of your variable, which is going to be the residuals of lm.fit1. And then you can see that it's actually pretty normally distributed. I mean, it looks like so, but I mean, this is just a graphical way of seeing it. So that's why we also do the QQ plot to see if it's, I mean, to be more sure of it. And then on top of that, we can actually add a QQ line, which is going to plot QQ line like this, and we're just passing the residuals to of our lm.fit1. There you go. And I'm just going to color it red like that. There you go. And there you have it. So I mean, the QQ plot for a normal distribution basically means that the more your points are aligned with this line, the more your distribution is actually normal. Okay, so this one actually starting to look pretty normal, and that's the graphical way of testing if your residuals are normally distributed. If you want to be even more sure of it, you can add another test. I mean, normality analysis is just a topic in and of itself, and it could take a long time to actually go through it. And there are very numerous and different kinds of tests, and not all of them work with all distributions. I mean, with all data sets, but I mean, I'm just showing you a couple here. You can also use a Shapiro test, Shapiro-Wilk test. And what this one does is that it basically just tells you if your distribution is normal. As well, we pass in the residuals of our linear model like this, lm.fit1. There you go. We run it, and there was a problem because I called it Shapiro instead of Shapiro. There you go. We run it, and there we have it. So the Shapiro normality test, what it does is that it assumes that the distribution is normal. Okay, that's the H0, and then we just run the Shapiro test, and if the p-value is lower than 0.05, that means that we reject H0, so we reject normality. Here the p-value is of course over 0.05, so we cannot reject H0 and the normal. I mean, so we keep the H0 hypothesis, and we keep the fact that it's actually normally distributed. So that was the normality analysis of the residuals. So they look pretty normal, and that means that our model is actually looking pretty good. So what are we going to do right now? We're actually going to evaluate the quality of the model by training it, because so far we have actually trained it using the entirety of our data. But what we're going to want to do now is we're going to divide our data into a training set and into a testing set. It's just, I mean, of all the 500 observations that we have here, we're going to take some random observations, train our linear model with those, and then we're going to create we're going to test this model and try to predict the values on some data that the model has not seen before, which is going to be our test data, and then we're going to see how well we did. Okay, so let's see that. I'm going to just add a new section right here. I'm going to call it evaluation of the model. There you go. And let's just set the seed for 1 right here, and let's just generate row number. And let's just create a sample from 1 to n row, the number of rows in data, and 0.8 times the number of rows in the data. Okay, so what are we doing right here? Let me tell you. So here what we're doing is basically we're just taking a sample from 1, and I mean we're giving it a range from 1 to the number of rows in data. So the number of rows in data is 500. So we're taking a sample from 1 to 100, and what we're going to be doing is we're going to be taking 0.8, I mean 80% of that data. And this is what we're going to, I mean this sample, I mean this is just like the list of rows that we're going to be using there for this one, okay? And it's going to be random. So let's run it right here, and here we have it. It's just an array, a list of of 400 elements, and it's random. Okay, so that's what I was telling you about. Now we're going to create our train variable with it, and for it we're just going to subset our data with this new oh sorry, I missed the comma right here. There you go. So what we have done right here is that from this random sample that we have created, we just subset our data. So now we have 400 random elements from data in our train data set. Okay, so there you go. Then we're going to do pretty much the same, but with the test data set, and we're going to call it test, and we're just going to subset again data, but here we're just going to add a negative before the variable right here. So we're just going to take exactly the opposite of this one. So let's just run that one, and you can see that our test is 20% of the data right here, and our training set is 80% of our data right here. So we have our training set and our test set. All right, so let's now, what we're going to do is estimate the linear fit with the training set. So we're going to do pretty much the same thing that we did before, but instead of using the entire set, we're going to be using only the training set. So let's do that. So we're going to do lm.fit, and before we just called it 1, but since we're now just using 80%, I'm just going to say 0.8, and let's just add it just as we did before, lm yearly amount spent. There you go. And then that's going to be our response, and our predictor is going to be length of membership. There you go. And I mean, since I don't think I have it attached yet, or I'm not sure. Yeah, I think it's attached still, so this should work. Oh no, that's actually not gonna work, because I have still attached, I mean, the one that I have attached is the data, and I don't want to work with the entire data. I just want to work with the train data set. Okay, so I rerun this, and now lmfit 0.8 is trying to get yearly spent from length of membership with the training data set. So it's using only 400 observations to train this model. Okay, let's take a look at the summary and let's see what we can see from it. Summary lmfit 08. There you go. So let's see, we have a pretty similar result to the one that we got using the entire dataset, and that is convenient because, I mean, we're using pretty much the same kind of data. But the thing right now is we're going to try to predict, taking the test dataset, we're going to take every single value from I mean, we're going to try to predict using something like this. We're going to take every single value of the length of membership and we're going to try to predict the yearly amount spent. And we're going to try to find how far off was our prediction. Okay, so let's do that. We're going to predict in the test data set. There you go. So what we're going to do is try to predict with this model that we have created to run the prediction in our test data set. Okay, so to do this, it's actually pretty simple. What we're going to do is we're going to just create a new variable that's going to let's call it prediction 0.8 because we're predicting with 80% of the data, and we're going to use the function called predict like that. There you go. And this function takes in two arguments. The first one is going to be your model, and the model is the one that we have just trained. So it's lmfit 0.8. Remember, we created it up here. And the second argument is going to be the new data that we're going to be using to actually test it. And the new data is the test data, of course. I mean, it's the remaining 20% data that our model has not yet seen. So there you go. I'm going to run it like that. There you go. So there you have our prediction 0.8. There you have it. It's just a list of 100 elements. And so, I mean, it's basically just what it predicts. Let me show you what it actually is. So what this thing is doing is it's taking the variable length of membership from our test dataset, and without looking at the actual yearly amount spent, it's trying to predict how much the yearly amount spent it was for that actual observation. So it's doing that for every single observation. So that's the reason why we have a list of 100 things right here, because it's the 100 predictions for the yearly observations for the 100 observations in the test dataset. Okay. And what we're going to do now is we're basically just going to calculate the difference between what was predicted and what was the actual value. Okay, and to do that, I'm just going to store that in a new variable called error 0.8. And I mean, it's basically just the difference. So it's prediction. I mean, this value right here, prediction 0.8. minus the actual value. So since we have a list, it's going to calculate the difference between every element in that list. And this one right here is going to be test yearly amount spent. There you go. And now we have our variable called error 0.8, and it's just a list of 100 elements of the difference between those. Between the actual value and the prediction. There you go. And now we can actually calculate some the error measurements. I'm not going to go over what these actually are, but I mean, just like you can look for an explanation of what these are. But I mean, they're used to actually check how well your model is behaving, okay, and how well it's predicting its results. So first, I'm just going to show you how to calculate the root mean square error. I mean, it's pretty simple. Just going to call it root mean square error like this, and I'm going to save it. It's pretty much just defined as the square root of the mean of every part of your error squared. There you go. There you go. So now we have our root mean square error that was defined. And let's also create an absolute percentage error. There you go. And that's the map. Mean absolute percentage error. And this one is basically just defined as the mean of the absolute value of error 0.8 between over test and the yearly amount spent. There you go. So now we have our map and our RMSE, and let's just take a look at those and what these look like. RMSE equals RMSE map equals map R squared. Let's also take R squared. So it's going to be equal summary lm.fit 0.8 tech squared. Pretty sure this is supposed to work. R2 mode. What's going on here? Summary lm fit 0.8 R squared. There you go. There is a problem with this one apparently. What happened here? Summary. Just gonna R squared. Just let me show you what's going on right here. So we have our root mean square error, which is 44. We have our mean absolute percentage error. Of course, since it's a percentage error is between 0 and 1. There you go. So this is pretty much how to evaluate your model. I mean, there are many different methods, but there you go. Those are just a few. R2. I don't know what's going on with R2. R2 length, R2 class, and R2 modes. No. Let's just check this out. Is there a problem with this function right here? Oops. Alright, so there seems to be a problem with that one. lm fit 0.8. R squared, multiple R squared. Alright, so we actually have the values. I don't know why it's not working there. No, it's actually alright. What was the problem here? Alright, sure, because I added this one right here. It was not supposed to be here, it was supposed to be here. There you go. So now it should work. There you go. So now you have R2. So now you have the three measurements in here. Sorry about that. So this one right here is the one that's actually creating the summary, and this one right here we're just subsetting R squared. There you go. So that was how to evaluate the model. But as you can see right now, the model is, I mean, it's alright, but it's not amazing. What I'm going to show you now is how to do pretty much the same thing, but with a multiple regression. So what we did so far is just like a regular linear regression with just one variable. But I mean, in the real world, there is not just one variable that influences your result. So in the real world, you're going to be using a multiple regression, even for the simplest cases. Because I mean, the world is not very simple, right? Let's attach our data again. There you go. And then what we're going to do is we're just going to create a new model. We're going to call it lmfit. And in this one, again, we're going to start with yearly amount spent. That's the first argument. Again, it's going to be the response that we expect. But after, I mean, remember that the second part of this formula after the tilde is going to be the predictors, okay? And instead of just adding one single variable that like we did before, we added right here we added pretty much just length of membership as a variable. And in this one, what we're going to do is we're going to add all of the other numerical variables, okay? So we're going to add average session length. Then we add plus, just going to add them in the same line, added time on app, we're going to add time on a website as well, and we're going to add length of membership. There you go. So now what this one is doing right here is it's training a linear model, but it's going to be a multi-dimensional linear model, okay? So basically our function is going to look more like this one right here. So we will not be working with a single variable linear model, but we'll be working with a several variable linear model. And we're just going to try to find which variables are actually relevant to our response. So let's take a look at that. To do that, what we're going to do first is, well, first of all, let's take a look at our summary of, just with this simple command, we have just already created our linear model for our multiple regression. So let's see how that looks like. lm fit. There was a problem with this one. Summary lm fit tag. There you go. So let's see what this looks like. So we have the formula that I showed you. We have the response expected and the predictors over here. And here we have the residuals as well. You're going to want to do, just as we did before, a residual analysis of this one too. But here, as you can see, instead of the single coefficient that we had on the previous linear model, here we have several predictors, okay, and we have several coefficients. So we have, for example, that the average session length has a coefficient of 25, so it's actually quite important. It seems to be quite important. We have time on app of 38 and the length of membership of 61. This one seems to be the most relevant one, apparently. But we also have more information right here. We have the standard error, we have the t-value, and importantly as well, we have the p-value right here. What does the p-value tell us? Just as we were mentioning before, it tells us that if it's lower than 0.05, we reject the null hypothesis and we actually keep the variable as significant. The 3 stars, as I was mentioning before, indicates the significance of the variable. So 3 stars is very significant, 0 stars is not significant. And as we can see from this multivariable linear model, we see that the time on the website is not a very significant variable, even though it has, even though we included it in our linear model, we can drop it, and it's not going to harm our model. So yeah, 3 of the 4 variables studied seem to have a positive impact in the response variable. Positive, because all of these coefficients are positive. If one of the coefficients was negative, that doesn't mean that it's not relevant, but it means that the correlation has an inverse relationship with our result variable. There you go, and of course time of website that we're going to be able to drop. I guess I can show you how to. Yeah, let's do pretty much the same thing as we did up here. I'm just going to copy paste the part of the evaluation model just to go pretty fast. But let's just evaluate this multiple regression evaluation of the multiple regression. As you will see, this one right here is actually way more accurate. So again, we're going to set the seed to 1, and we're going to be working with the same train and test data set. We're not going to recreate our division, but what we are going to do is we're going to create our linear model for only the training set, our multi-variable linear model for only the training set. So I'm going to copy this line right here. I'm going to paste it right here. There you go. So what this one right here is going to be doing, I'm going to be calling it 0.8 as well. And what this one right here is going to be doing is it's going to be, again, just creating my linear model, but the data that we're going to be using for this one, there you go, is going to be the train data set. Oops, train data set. What's going on here? Train data set, there you go. So I'm just going to run this one and let's see how that looks like. So as you can see right now, it's pretty much the same as we had before because we're using the same kind of data, but now what the important part right here is going to be the prediction. So we're going to use this lmfit08 to predict the new data of the test dataset. Okay. You know what? I'm just going to change the name of this variable so that it's easier to see. I'm going to call it multi-linear model fit. Just run it. I'm going to call it, there you go, multi-linear model fit. There you go. And then we're going to predict it. Here I'm going to be using the multi-linear model as our predictor, and the new data is going to be test, just as before. And let's see how that worked. Again, just as before, we're going to be calculating the error. And the error for this one is going to be stored in prediction 0.8 minus the actual value in the yearly amount spent. Let's run that one. And again, just let's run the RMSE, MAPE. There you go. And let's just print that out. So there you go. So here you have the results for the multiple linear regression. I hope I didn't lose you in that one. I mean, we did exactly the same thing as we did with evaluating the linear model for a single simple regression model. But we just did it, I mean, it's pretty much exactly the same, just that we added more variables here as the predictors. And as you can see, the results are different. The error measurements are much better. R2 is almost equal to 1. And that's pretty good because we're working with the test dataset. And as you can see before, we had used a multiple regression. Where is it? Here it is. These were our previous values for the root mean square error and for the mean absolute percentage error, and for R squared. So as you can see, the error right here went from $42 to $8. The mean absolute percentage error went from 0.07 to 0.01, and R2 went from, R squared went from 0.65 to 0.98. So we have improved our model by a lot, and yeah, I mean, that's pretty much how you run multiple regressions in R. So yeah, I mean, the findings are that by using a multiple linear model, we have created a much more accurate predictor of the response of the variable. Even though we're using a pretty simple mathematical tool, we're actually being able to predict much better and to explain much better the data by using a multiple regression model. So R2 went from 0.65 to 0.92, RSC went from $47 to $9. So pretty good. All right, so there you go. That was how to create a multiple linear regression and how to train a linear regression model in R. Hope you found it useful. There you go. Please like and subscribe if you liked it, and I'll see you next time.